not interesting. It's more because of a little bit of the logistic. I also struggle to find the entrance, and some more people are coming as well. So very good. We can start. Thank you. So transducers, a funky name. It has, I think at the core, they are a simple abstraction, and we're going to see this abstraction and going through that. A little bit about me. I'm a developer at USwitch. It's a company in the UK, based in the UK. I'm writing a book in my copious spare time. It's a guide to the Clojure standard library. It's kind of a monumental book. It's going to be 1,000 pages. Eventually, I'm going to arrive at the end of that. There's a discount code if you're interested in that kind of things. I'm also author of screencasts. Those are on YouTube. If you search for Clojure pills, you find the Clojure pills, a very nice 20-minute pills about one function of the standard library, and they're teaching you about Clojure in the process. I'm co-organizer of the Paper We Love meetup in London. And if you have any questions, you want to get in touch after this conference, I'm very happy to listen to you. That's my email account, and also @Reborg is my Twitter handle. Okay, so transducers. They are a fundamental abstraction, a functional abstraction, like maybe similar to patterns in object orientation. They decompose sequential processing and they recompose it so that is modular and independent. It's inspired by the universality of fold. There's a paper about that, and there are the links at the end. In the fact that with fold you can express many of the sequence processing operation. It was introduced a while ago in Clojure. I think it's mildly underused, and I think it might deserve more attention. That's why I'm bringing it to you today to have a look. It's also because it's available in many other languages. And I'm going to talk about a few of the tricks and experience with transducers on production application I had in my projects. So compared to like passing a lambda to a map operation or on top of a collection that you want to process, they are more composable. They can compose with comp instead. In Clojure you'll force, so to speak, with a threaded operator, which is a macro, to compose them up. For this reason, they are also more reusable. You can adapt them to different transports, so you can use them in the collection that the standard library is giving you, but you can also use them on other things. It's also faster because it removes the intermediate sequencing, and it's also easily parallelizable. And we're going to see all of this today. So why are we even talking about this if it's so great? Because there is this common thinking that you might need them only in certain particular cases. Instead, I think they're more universal. And people are already used because they enter Clojure so late that people are already used with like a sequential processing the standard traditional way, so they are more reluctant to change, to jump on something different. There is something else in Clojure called reducers, which has a name which is similar to transducers, so it remembers something that is instead specific. So people are maybe confused, and they are introduced late. So let's go through an exercise now. I think I might have jumped this one first. To try to find these four aspects in sequential processing. We'll go through map and filter, which are easy functions to define and to see, and we're trying to see where those aspects are and if we can extract them apart and build something different with them. So we're going to see access to a specific data type, and in Clojure it's first or rest on a list, for example. We see the accumulation of the results, for example, with operation like cons, conj, plus if it's a reduce. A recursion mechanism, because these functions are recurring in one way or another. They can do it implicitly with the stack, with an implicit stack, or explicitly in an iterative way. And the essence of operation itself. So if you're mapping, we want to increment each number in a collection. Inc is the essence of what we are doing. So let's grab one example. I hope you can all see over there. I thought it was big enough, but it's not. So in this map, we can say in this map operation, which is taking a function and a collection, and that is the implementation of map, those circled in orange are the type-specific interface. So it's using some kind of API, and that API is dependent on the collection. So the collection needs to know, how do you give me the first element? How do you give me the rest of your elements? Or when the collection is empty, I'm saying it's equals to the empty list, for example, and that is specific. You cannot use that with another data type. Then we have the building output part. That's conj there, which is taking the map of F on the rest of the collection and is attaching that to implementing the operation F, in this case, to the first element in the collection. That is building the output, increasingly building the output. Then we have the recursion mechanism. We have an exit condition. When it's not that, recur. If it's that, don't recur, because if not, we go in an infinite loop. And of course, we are invoking ourselves. Map is invoking map again. So it's a very simple case of recursion, but it is fine for the example. And finally, the transformation. So there is where, if we say we want to increment each number in the collection, that F is going to be an increment operator and F is applied. So these are the four aspects. Let's do the same exercise again on filter, slightly faster. Try to see if you can see those four aspects yourself. So type abstraction, where is the type abstraction here? We still have, again, first, rest, and not equal to an empty list. Similarly, we are building again the output with conj. We have same recursion mechanism. When some exit condition is met, stop the recursion, if not recur, and filter, calling again. And now the only thing that is really different is the mechanic of filtering, which is if some predicate is true, then let the this item through the results. If it's not, don't let it through the results. So this is what really changing between map and filter. And then we can go, and you don't need to understand this, but just to show you that if we had to implement the same mechanism as we have to for other transports, which are not collections, like lists or vectors, this is, for example, a channel in CoreSync, which is a concurrency mechanism in Clojure. You want to do similar things. You want to map or filter elements going through a channel or coming out a channel. And so you'll have to kind of reimagine how would you do that on top of a different transport. And here we are again. So you don't need to understand this, but I'm going to tell you that is the data type interface, extracting from an input channel, sending down to an output channel, checking if the channel is closed, and so on. Map is at the top, filter is below. And again, this is building the output when we send things in the output channel. This is the recursion mechanism. Is slightly different than before. There is this go loop macro, and there is the recur, but it's similar. It's doing like do it again until there are elements in the channel. And finally, these are the essence of the different transformation. We have a transformation at the top, and we have a filtering operation at the bottom. And you can see they are the same, but they are kind of decorated with a lot of things around them, which is different than before. Final exercise. There is another library in Clojure called Clojure RX, which is implementing observable, reactive programming, and they have sort of similar to channels. They are called observables, and you can observe a stream of events coming through. And you want to do similar things to this stream, like you do to the channel, like you do to the collection. You want to map stuff, you want to filter stuff, and many other operations. Once again, data type, subscriber on next, building the output, doing with this lift thing. I'm not sure 100% how it works because I'm just a user of this library. And recursion mechanism is creating this operator that is then given to the lift operation. And once again, and is the same as before, transformation for map and filtering for filter. They are the same operation, just all the surrounding has changed. So what happens is that there are not just map and filter, there are all sort of possible sequential operations. The more you have, usually the more you are expressive in your language. So your language may have many more or different ones. In Clojure there are some of these, and there are more than that. So if you imagine to implement this on top of each different transport every time, what we get is a combinatorial explosion of some sort. Right? There are too many aspects conflated in map or filter. We need to do this again and again and decorate with different code. What if you wanted the same transport? So the same operation on different transports, which is what we want to achieve. So essentially what I'm asking is, how can I extract the essence, the transformation or the filtering from those operations so I can reuse them in other contexts? And this is what we are going to do now in a few simple refactoring operations. And what I think is the discovery in this case is the reduce operation. So reduce operation is essentially a pattern for recursion. It is a recurring operation. It is iterative because the results are built and passed through the arguments. So you can see that is reducing is calling itself, is passing the function that it received, and it's also passing the results. So it's accumulating them and it's passing them on the parameters. So it's a different kind of recursion, but it's a recursion. And it works reasonably like that's an example. You want to sum up all the elements from 0 to 9, it is 45. You pass the plus operator, which is the reduction function. So the discovery is that when you start to build the results or to build those operations on top of reduce, you can extract the essence of the operation. Let's see how it is done. And all right. So this is map, the same operation as before, but built on top of reduce. Let's visualize what are the operations that we discovered before, when we were looking at before. So the essence now is in the caller of that function, because we need to pass it in the function. So it came down, and map is above there. Building the output also came down into the caller of the function, because the way reduce works. And the data-specific types are still inside the mapping function, what we call map there, which is a reducing function. And if we look at filter, we see the same things. We can rebuild filter on top of reduce. And when we do that, the function that we need to pass to the caller that needs to create this function needs to pass the function to the filter operation, now embeds the essence of the essence of the filtering. So in this case is a condition. If the predicate is true, then move on. Same for building the output, conj, and the vector.
Quick question. You're building filter on top of reduce, but I don't see any calls to reduce.
No. So
I'm puzzled.
yeah, next slide should.
Okay.
So the two functions, the one that we called map and filter, and I said they are built on top of reduce, are reduce. So I just changed their name. They are the same. If you overlap them, the only thing that is changing is map and filter. If you replace that with reduce, that is reduce. So we are just using reduce to build them. You can, if you put reduce on that, it's going to be reduce. Is it? It is a reduce operation. If this is reduce, that is reducing with f, the reducing function, and that is f applied to the result and the accumulated result so far and the first element of the collection, and that moves on. So that is reduce in Clojure at least. So as I said, the caller is now embedding those two. What is still missing? So if you look at that, we are still embedding the essence of the operation there. We want that to be generic. So today is an increment, tomorrow is a decrement. It could be something else, or the predicate is odd. It's just an example. That should be really an F. So, and the other thing is the accumulation of the output is specific to sequential collection, is a conj, also that is specific. I want to extract that out, because if I remove those two things, what I have in my hands is just the essence of mapping or reducing. So let's see how we can do that. We just wrap it in an anonymous lambda. Sorry, yeah, it's an anonymous lambda. We wrap it, and then we call the lambda the way we did before. So we extract. In this case, we are extracting the output accumulation. We call it RF, is a reducing function, and now that appears here as a parameter, and this is returning a function of results and of an accumulation and the next element. That is the reducing function that we had before, and just wrapped it with anonymous functions around. And we can do the same for the other piece that is specific, which is the transforming operation or the predicate or any other kind of operations that you're doing. And we do the same operation again. We wrap yet another lambda function. This time the lambda function, so we have two of them now. This is the reducing function, accumulator and element. This is extracting the reducing function, which was the conj. And this one is taking the predicate, or f, that was instead, before was embedded inside. So we have two constructors for a mapping function and a filtering function. Final step, we are done. So with those two definitions, we place them in reduce, and we can use it as before. So we have a mapping increment on range of 10, and filter odd on range of 10, and they work exactly as before. So what's the difference? Let me show you something before we go. So the difference is that now the essence of the operation is a parameter that you pass from the outside, as well as the accumulation of the output. So when you have these two things extracted out, you can use them in different transports. Now we're going to see a few examples. When you do that kind of abstractions, you can start doing these kind of things. So this is a very long chain of those transducing functions. So they are similar to map and filter there, and they are at the top, map inc, filter even, and there are a whole bunch of them that are doing that kind of thing. Since they have the same contract, so they are reducing function, they all take an accumulation and an element. It means that they can be composed with comp, so it's just functional composition. Each one of them is returning a function of two arguments. You can compose them all. So that whole chain of comp is doing all those things. But that is quite long, maybe not very reusable or difficult to understand. But now that you have comp, you can just take it apart. So that is essentially enabling you in your program to have very long pipeline, data pipeline, processing pipelines, and you don't need to think about how do I decompose them, because they are too long, I don't understand, they are difficult to debug. If you have comp to do these things, you just tear them apart. So that is the same chain we saw before. I'm just taking like 4 functions each block, give them a name, still using comp, and recomposing everything down here. So this is the same as that, but it just contains 2 compositions. So you can apply comp on top of comp on top of comp as many times as you want, and then you can split these things apart. So they are different concerns. You can test them separately in isolation. It would be difficult to do it with like traditional sequence processing based on macros, the threaded operator. This is the concurrency facility core sync that we saw at the beginning, and now that you extracted the essence, extracted the accumulation of the output, you can use the same old X form. So again, composition of filter, odd, mapping, just as an example, and you can attach it to completely different transports. As you can see, you don't need to understand what this is doing, but that channel that I'm creating there, anytime it's receiving an event or an item, is going to apply the transducer chain to that, like if it was a sequence. or a collection. Another thing that it was helpful was to use this composition to introduce debugging and tracing. So if you have a long chain of in a traditional sequence, you resort to like do manual editing of that chain to introduce print line, or maybe stop the programming at some point so you can see what's going on in a certain stage of the pipeline. But if you have the composition through comp, you can just assemble that in a different way. So just want to talk about this before. So this is the X form, like before. The only thing I changed is I suspended the use of comp. So it's just a list of those reducing functions. Comp will be applied later on. So now that I have this power, I can just treat it as data, essentially. And what that DBG X form is doing is a transducer itself. It's just not one of the core ones. It's a custom transducers that it can be interleaved into this list. So when each item passes through the pipeline, I can trace it. And that is happening with a wrapper that I'm showing there, where that DBG X form is interleaved to the X form. But I think what is important to know is when I run it, I can see what's going on. And I was able to assemble that at runtime. It wasn't like statically in code in any way. So I can do that based on a parameter that is coming in the program. If the bug is on, I can start tracing things through the data pipeline. Now going parallel, about talking about parallelizable things. Since there is a facility in Java that Clojure can use, it's called fork join, it's part of the JDK. And this facility can be seen as yet another kind of transport. So when you give it a vector, this facility is able to chunk it up into pieces, send it to different cores, to different threads, depending what you have, and then assemble it back together. So if we agree that that is a different kind of transport, and we want to go parallel with our transducer that we saw before, that chain of many things, we can just apply it to the new transport. And how do we do that? We do that with something else that is, again, inside the Clojure standard library. That is called fold. It's enabling this fork join mechanism. And my X form, the usual old X form is here. And I can apply it here by just passing what should be like the accumulation function. In this case is a conj. You don't need to follow exactly, but it's passed through here and it's coming down there. And when I do that, that becomes a reducing function, and this fold will take care of chunk the collection up into pieces of 512 by default, and just making it explicit pieces, sending them in parallel, do the computation. Each transducer chain is going to execute on a single core. The result is going to be combined back with vector. I think the takeaway is that this X form is yet again the same thing, and I'm using it in different contexts. Said that is. So a final remark about speed. So I said also that they are faster because they don't produce intermediate collections, and this is what I call the traditional sequential processing, which is chaining them up. So they look very like the same, but you see there is the arrow operator at the top that is doing the concatenation. So when you do that, each one of those operations will go through the data and then pass the transform data to the next that will go again through the data, and so on and so forth. So each of those lines is a pass through the sequence in its entirety. What transducers does, they work differently. They compose all the operation into a single big composition that is doing all at once to a single element. So the sequence is scanned only once. And for that reason, this is a very simple example with no data essentially, just 20 elements or so. And it's roughly 50% faster. So the more your the more your data pipeline is doing, the more advantages there are in making it parallel. And since you don't need any library to do that, you just need to require a couple of things, you can do it quite easily. It's really available. So that is powering one of the parts of our website. There are these feeds of 10,000 mortgages, and these mortgages are huge maps with a lot of keys and a lot of values in them, and they need to be processed. There are at least 10 filters. Some financial math calculation need to happen. They are quite intensive. By doing all of that through transducers and going parallel, it went from roughly more than 10 seconds per request down below 2 seconds. And those are like conservative estimates, in the sense that it's an average, but I think is faster if you measure it not at the web level, but at the transducing chain level. I think that's all. So these are a few links. So I appreciate that. I mean, you might not be used to Clojure and a few of the technology I mentioned. So I hope you could still grasp a little bit of what I said. Those links will help you out. The two presentations by Richiki about transducers are a gentle introduction that I recommend. The two papers I'm mentioning there are more rigorous, and they are essentially responsible for the introduction of transducers. Sorry, they are responsible for the concepts inside transducers that were introduced in Clojure. Finally, there are a few interesting projects that are expanding on those ideas. Xforms at the top is collecting a few of those transducers, some that are not yet in the standard library, or maybe perhaps will never be. The reactive extensions I mentioned, transducers in other languages. So after they were announced, many people were at least curious about understanding what they are, and they went on and translated them in their own language. And it turns out it's possible to do it in many languages, and I'm mentioning 3 of them, and there are others. So they were also done in Haskell. As usual, I think when you mutate an abstraction from one paradigm to another, you learn a lot in the process. Most of the time, the abstraction in the new paradigm is not as powerful as the originating paradigm. So my guess is that Haskell transducers are not that used because there are other abstractions that are matching much better for Haskell. That's my guess. That was all. If there is anything, any question, I'm happy to answer now, later on at the party. Thank you.
Look, I know there's not typed, you didn't say anything about type, but nevertheless, if I'm looking at that comp, right, I'm clearly composing together some components of these transducer things, right? So can you tell us anything about what the type of map ink is? I mean, it's not what it used to be. It's a new sort of map, isn't it? It's not map over list, because it's collection independent.
Yeah,
so
you don't know.
Tell us anything about, I have no idea about, just the function, right? So
yeah.
take arguments
is
that look like something. I don't even know how many arguments it takes. I missed it, how many lambdas it had.
Yeah, well, they are variadic, right? So there are like.
So what does a transducer look like? So these transducers, they're all the same in some sense, right?
Yeah.
Otherwise,
yeah.
not good for person. So what's their type?
Exactly. So I mean, what I can tell you is the kind of function they're returning, which is what make compose to work properly.
Function of some type.
Yes, is the signature of reduce or fold is a function of an accumulation. You don't know the type of that accumulation. It could be anything, and so the accumulation is a list. So a function of a list and an element, which is instead a scalar.
If it was a list, then it wouldn't work when you gave it reactive, right? So these.
List. Take list not as a specific. Yeah, don't take list as a specific list. Not a list. I should talk about collections in general. So it's a function of a collection and an item, and the only thing you know is how to use them. Like is a reducing function. So the function you use to accumulate needs to obey this rule. So it will take two arguments, and you are supposed, but nothing is forcing you in any contract. You are supposed to take the accumulation, the item, do some transforming operation on the item, and put it back in the accumulation. It might work. I mean, the compiler cannot tell you anything about what's going on in there. If you send it down garbage, you will receive back garbage of some sort.
I'm maybe asking a simpler question than the one you answered, which is, in this list of transducers, how many arguments do they take? So each transducer presumably is a function.
Yeah. When you say transducer, you're saying like the result of the evaluation.
Yeah, those things.
The result of the evaluation of this.
Yeah, those things, because they're all the things that comp is composing.
Yeah,
right?
that is returning a function
Of how many arguments?
of two arguments.
Two. Okay.
Yes.
And those arguments are each transducer is a set chain.
It's the collection and the item.
Oh.
Yeah, I mean, it took me a while. It's 3 years in, right? And I'm talking about you today. And it took me a while to use them. I just wanted to show you when we did that abstraction, right? When we do map of that ref, what is returning is a function of two things. I hope it's clear.
So you said map inc. Inc is RF.
Yes.
But
Oh,
inc
wait.
was
No,
thought
sorry.
was
No, we
going
did another step after that.
Oh.
Map inc is that. Oh, okay.
Oh, so it takes 3 arguments. Aha.
You're right.
East.
Confusion on my. When you call map of f, it's returning an f of one argument. So this is what returns.
Right, which then returns a function of 2 more arguments.
Yes.
So 3 altogether.
Yes. So the big concatenation there is on top of a function of one argument. And then the reducing function is applied at the end, conj, for instance. Any more? Please.
What are the downsides of the real world applications when you get patterns or
So there are a few things to consider regarding like big data. You cannot load terabytes of data through a transducer chain like I'm doing apparently here. So you have a few things you can do, depending on the kind of computation you have to do. If you go parallel, that chunking is helping in splitting like bigger collection into multiple pieces. Over a certain size, I think, though, you'll have problems unless you have thousands of cores. But I think at that point, you're scaling the wrong way. You should probably scale horizontally with more machines and not trying to scale on CPU cores. Because there are just some finite number of them, and usually it's not huge at this point. So even if you have 1,000, if you have terabytes of data, you cannot. I wouldn't suggest to go with a transducer chain and split it in parallel over the multiple cores anyway, because it might still be too big to do. But at least at that point, what you can do is to delegate at the transducer level the loading of the chunk of data. So you can decide how big the chunk is. So maybe if you cannot do it in the first pass, you can do it another pass after that, and like apply the reducer in a loop on until you're done, essentially. So yeah, that will be a limit. Yes, please.
was it hard to, because I have to how hard it is for other developers to grasp this concept, so how was
Yeah, we kind of like at the same level. So we all look at new technologies as they come out and we experiment with them. So there was no real step of introduction. People are sort of expected to know that there is this new feature. If you don't know it, you ask, and then we'll probably go through something like this. If you really want to understand how it works, the inner side, the inner part of it, we'll probably do something similar to this. Because I think as refactoring steps are quite easy to do. The final result is still some learning curve if you don't know the concepts. But still is functional composition and a couple of lambdas on top of each other.
Just by curiosity, your web function or composition, is it needed in your trial? Is it?
Yes. Yeah, it is. It is connected to. Yeah, you won't be able to use it from the outside. So if you pass ampersand trace equals true to the website, it will trace. And you can trace one like ID at a time. At least this is what we needed. Then you can do what you want. All right. What's next? I think it's the break.
Yeah, so it's a coffee break, so it's 20 minutes till the next time.
Okay. So I was on time at the end. No, unless there are other questions, I'm done. Thank you very much. It's a guide to the Clojure standard library. It's kind of a monumental book. It's going to be 1,000 pages. Eventually, I'm going to arrive at the end of that. There's a discount code if you're interested in that kind of things. I'm also author of screencasts. Those are on YouTube. If you search for Clojure pills, you find the Clojure pills. A very nice 20-minute pills about one function of the standard library, and they're teaching you about Clojure in the process. I'm co-organizer of the Paper We Love meetup in London. And if you have any questions, you want to get in touch after this conference, I'm very happy to listen to you. That's my email account, and also @Reborg is my Twitter handle. Not interesting. It's more because of a little bit of a logistic. I also struggle to find the entrance, and some more people are coming as well. So very good. We can start. Thank you. So transducers, a funky name. It has. I think at the core they are a simple abstraction, and we're going to see this abstraction and going through that. A little bit about me. I'm a developer at USwitch. It's a company in the UK, based in the UK. I'm writing a book in my copious spare times today. So why are we even talking about this if it's so great? Because there is this common thinking that you might need them only in certain particular cases. Instead, I think they're more universal. And people are already used because they enter Clojure so late that people are already used with like a sequential processing the standard traditional way, so they are more reluctant to change, to jump on something different. There is something else in Clojure called reducers, which has a name which is similar to transducers, so it remembers something that is instead specific, so people are maybe confused, and they are introduced late. So let's go through an exercise, tricks and experience with transducers on production application I had in my projects. So compared to like passing a lambda to a map operation or on top of a collection that you want to process, they are more composable. They can compose with comp instead. In Clojure, you'll force, so to speak, with a threaded operator, which is a macro, to compose them up. For this reason, they are also more reusable. You can adapt them to different transport, so you can use them in the collection that the standard library is giving you, but you can also use them on other things. It's also faster because it removes the intermediate sequencing, and it's also easily parallelizable. And we're going to see all of this. Okay, so transducers. They are a fundamental abstraction, a functional abstraction, like maybe similar to patterns in object orientation. They decompose sequential processing and they recompose it so that is modular and independent. It's inspired by the universality of fold. There's a paper about that, and there are the links at the end. In the fact that with fold you can express many of the sequence processing operation. It was introduced a while ago in Clojure. I think it's mildly underused, and I think it might deserve more attention. That's why I'm bringing it to you today to have a look. It's also because it's available in many other languages. And I'm going to talk about a few of the